All right, we're going to start with an easier question. How many ways can I roll 4 dice so that 2 of those dice sum to the number 4? And one idea that's just going to be kind of easier when we're dealing with this is we're going to think of all the different pairs, and we're going to say unordered pairs that sum to 4. And the good news is there's not a lot of them. That's why we're starting here. The only ways that I can sum to 4 are using the numbers 1, 3, or using the numbers 2, 2. So this reduces to kind of 2 separate questions. How many ways? Well, it reduces to 2 separate questions and then a little application of inclusion exclusion, which is, why we're doing this video. Anyhow, I first am going to ask, how many ways can I get the pair 1, 3? Then with a little less space, how many ways can I get the pair 2, 2? Let's start with 2, 2 because it's going to be a little easier. So let's think about it. What could my different numbers look like? Well, what I could do is I could roll, and first of all, even though all the dice look the same, they are each distinct dice. So when we're thinking about different combinations, it's good to think of them as different. Order will matter in which die gets which result. So if it helps you, it might think of these as like colored dice. Each one's a different color. So how many ways can I get the pair 2, 2? Well, one way I could get that is I could get 2 2s and then 2 different things. When I'm using the question mark, I'm specifically saying something I haven't seen yet. So it's basically anything but a 2. And that's important because we don't want to do some double counting. While we have ways to deal with double counting like inclusion exclusion, this is a case where it's a lot easier if I can kind of just split this up into exact cases that I know exactly how to handle and then add them all up. So what I'm going to do is I'm first going to do exactly 2 2s, and then we'll look at what happens if I roll exactly 3 2s, and then what happens if I roll exactly 4 2s. Those are kind of the different ways that I can do this. So what are the numbers on these? How can I think of this in combinatorics language? Well, in this first case, I'm going to choose 2 dice to have the value 2, and then the 2 remaining dice are going to get some other value. So there's 5 possible values, and there's 2 dice, so that's going to be 5 squared possibilities. This will be 6 times 25, which I think is 150 if I'm good at math. So there's 150 ways to get this result. What about the next one? Now I'm choosing 3 dice to have a 2, and then there's going to be 1 other die that has some other number. So that's going to be 4 times 5, which is 20. And then, last but not least, I'm choosing all 4 dice to have the value 2. There's only one way to do that. So if I total all of these up, I'm going to get 171 different ways to do that. So keep in mind we're adding. Since these are all distinct cases, if I want to find all the different ways to do this, or this, or this, I'm going to add up the numbers. 150 plus 20 plus 1 equals 171. Okay. So now that we've kind of warmed up with that, let's get to the harder question. How many ways can I get the pair 1, 3? Well, one way that I can get it is I can have a 1, and I can have a 3, and then I can have 2 other things. Or I could maybe have 2 1s, and then a 3, and then something else. Or maybe even 3 1s, and then a 3, and then some. Oh, well, then I can't have something else, because then we're out of dice. I can't have 4 1s, because I do need to have at least 1 3. But, you know, I could have, instead of having a bunch of 1s, I could have a 1 and maybe 2 3s. Could have a 1 and maybe 3 3s. And then last but not least, I could split down the middle. I could have 2 1s and 2 3s, and that would do the job. So how many different ways are there of doing each of these? Well, for here, I'm choosing, and I'm going to be a little silly about how I do this. I could just go 4 times 3 times 4 times 4 and be done. But, you know, I want to think about this carefully. I'm going to choose 1 die to be a 1. And then of the remaining 3 dice, I'm going to choose 1 to be a 3. And then I have 2 remaining, and they can be anything but a 1 or 3. There's 4 different ways to do that, so it's going to be 4 squared. Okay. And the next one, I'm choosing 2 of my dice to be a 1. And then of the remaining 2 dice, I'm choosing 1 to be a 3. And then the remaining can be anything. Here, I'm choosing 3 of my 4 dice to be a 1. And then I'm choosing 1 of the remaining dice to be a 3. Here, I'm choosing 1 of my 4 dice to be a 1, and 2 of my 3 remaining to be 3s, and then a 4. I'm going to take a quick note to say that this is pretty symmetric to what we did in the second case, but we did very different math. It turns out we're going to get the same answer, which is kind of cool. And if we didn't get the same answer, then there would be very big questions about what we're doing in combinatorics. So anyhow, and then this next case again looks similar to what we did before. We choose 1 of the dice to be a 1, and then of the remaining 3, we choose all 3 to be 3s. And last but not least, we split down the middle. We choose 4 of my dice to be 2, and then of the remaining 2 dice, we choose both of them to be 2s. So how many different ways are there to do all these? This one's going to be 4 times 3 times 16. I'm not going to calculate all of these specifically. I did this math in advance, so I wouldn't have to here. But this is going to be 6 times 2 times 4. This is going to be 4. This is going to be, you'll notice this is 4 times 3 times 4. So those 2 cases, I'll point out, these are both 48. So it's nice that even though we kind of went about the problem in 2 different ways, we got the same answer. This one is just going to be 4 ways, and then this one is going to be 6 ways. And if you total all of those up, which I did in advance, you're going to get a sum equal to 302 ways. So, I'll give myself a little bit more room here. You might be tempted to say, great. Our answer is just going to be 302 plus 171, which is 473. Not factorial, just we'll calm down a little bit. It's going to be 473. Wonderful. Except that's not right, and I want you to take a little pause the video if you need to, and try to figure out why isn't that right. Okay, the reason that isn't right is because it is possible. What if we roll 1 3 and 2 2 at the same time? Well, I can certainly do this. I can do that by rolling exactly 1 2 2 3. And if I roll both of those at the same time, I counted that in this category, and I counted that in this category. So I counted it twice. Inclusion exclusion tells me that I need to subtract it away in order to get my final answer. Well, how many ways are there to roll this? Well, I'm going to choose 1 die to be a 1, Of the remaining 3 dice, I'm going to choose 2 to be 2s. And then the last die, I choose 1 to be 3. It's a little silly to say it that way, but it works. And there's going to be 12 ways to do this. So let's cross that off, because that was wrong. But, now we're figuring stuff out. Our actual answer is going to be 302 plus 171. But then due to inclusion-exclusion, I now need to subtract the different number of ways that I could get both a 1-3 and a 2-2. There's 12 of those. And when I do that, I'm going to get a total answer of 461 different ways to roll a 4. Okay, so we saw a little bit of inclusion-exclusion there. Now it is your turn to do a similar problem before we spice it up a little bit more.